Let's solve a second order homogeneous constant coefficient linear differential equation that produces a characteristic equation that has distinct real roots. So here's an example. Second derivative of y minus first derivative of y minus 6 times y equals 0. Remember, the guess that you make to solve this kind of equation is that y should be e to the mx, in which case y prime is me to the mx, y double prime is m squared e to the mx. And when we plug this in, we get m squared e to the mx minus me to the mx minus 6 e to the mx equals 0. And everything has a factor of e to the mx, so you can factor that out. You get m squared minus m minus 6 times e to the mx equals 0. And then you can divide both sides by e to the mx, and you get m squared minus m minus 6 equals 0. Now, before we finish solving this, I want to point out that there's a really quick shortcut to get the characteristic equation, which is this guy down here, characteristic equation. There's a quick shortcut to get the characteristic equation from your differential equation, which is, if you compare these two, it looks like all of the derivatives just turned into factors of m, and whatever the order was on a derivative, that becomes the power of that part. So here we have a 0th order derivative of y, and that turns into m to the 0, which is just 1. Here we have a first order derivative that turns into m to the first, and then a second order derivative turns into m to the second. And the coefficients here, 1, minus 1, and minus 6, those are the coefficients down here, plus 1, minus 1, and minus 6. So in the future, we won't really need to write out all of this algebra to get the characteristic equation. We'll be able to go from the differential equation directly to the characteristic equation all in one step. Okay, so our characteristic equation again was m squared minus m minus 6 equals 0. We need to solve this for m. We could use the quadratic formula, but this one happens to factor. This is m minus 3 times m plus 2 equals 0. And so we get, right, one possibility for m is plus 3, and the other possibility for m is minus 2. And remember, each possibility for m gives us a solution to the differential equation. So our first solution is e to the first possibility for m, that's 3 times x. And then the second solution, y sub 2, is e to the minus 2 times x. So the general solution would be, remember in general it's c1y1 plus c2y2. And so in this case, this is going to be c1 e to the 3x plus c2 e to the minus 2x. Now actually something we need to be careful about is we got these two solutions here, but are they linearly independent? Remember, what we wrote down here for the supposed general solution is actually only the general solution to the differential equation if these two solutions, y1 and y2, are actually linearly independent. And also remember that we have a quick way of checking if they're linearly independent. We can just check that the Wronskian is 0. Now, if you know a little linear algebra, you'll know that just by looking that these aren't linearly dependent. These must be independent, because when you have two vectors and one is not a multiple of the other, then they're linearly independent. But let's just check that they're linearly independent using the Wronskian. So remember, the Wronskian is the determinant of, now we make our little matrix, so y1, which is e to the 3x, y2, which is e to the minus 2x, and then their derivatives go in the second row, so 3e to the 3x and minus 2e to the minus 2x. So now calculate this determinant. So the positive, or the product on the forward diagonal So e to the 3x times minus 2 e to the minus 2x, and then minus the reverse diagonal. So minus e to the minus 2x times 3e to the 3x. And this is going to give us, let's see, minus 2 times e to the 3x times e to the minus 2x is e to the x. Minus 3 times e to the x. So this all comes out to be minus e to the x, and that's never 0. So this solution that we wrote down really is the general solution because it's a linear combination of a fundamental set of solutions.